classical teleportation is very easy. When it comes down to quantum states, there are physical rules which say you cannot copy them. Quantum teleportation has been a concept that has captivated scientists and the public alike for decades. The idea of instantly transferring information, energy, or even objects from one location to another without any physical medium sounds like something straight out of science fiction. But as we delve deeper into the strange and counterintuitive world of quantum mechanics, we begin to see that such phenomena may not only be possible but are, in fact, happening right now. After 27 years of tireless research, experiments, and technological advancements, quantum teleportation has finally been achieved in a groundbreaking way that redefines our understanding of communication, computing, and the very fabric of reality itself. To understand the significance of this achievement, let's start at the beginning. What exactly is quantum teleportation? At its core, quantum teleportation is not about transporting physical objects or people as popular media might suggest. Instead, it involves transferring quantum information from one location to another instantaneously without physically sending the particles carrying that information. It is a phenomenon rooted in one of the most mysterious aspects of quantum mechanics: quantum entanglement. Quantum entanglement occurs when two or more particles become interconnected in such a way that the state of one particle is instantly correlated with the state of the other, no matter how far apart they are. This means that if you measure one particle, the state of its entangled partner will change instantaneously, regardless of the distance between them. Albert Einstein famously referred to this phenomenon as spooky action at a distance, and for years it remained a theoretical curiosity. In 1993, a groundbreaking paper by scientist Charles Bennett and colleagues outlined a theoretical framework for using quantum entanglement to achieve teleportation. They proposed a method by which the quantum state of a particle could be transferred to another particle at a distant location through the combined use of entanglement and classical communication. This laid the foundation for the field of quantum teleportation and sparked a wave of research aimed at turning this theory into reality. Over the past 27 years, quantum physicists have conducted numerous experiments to test and refine the principles of quantum teleportation. Early experiments demonstrated the feasibility of teleporting quantum states over short distances, typically within a laboratory setting. These initial successes relied on entangling photons, the particles of light, and transferring their quantum states from one location to another. However, achieving quantum teleportation over greater distances presented significant challenges. The fragile nature of quantum states, combined with the limitations of current technologies, made it difficult to maintain entanglement over long distances. The phenomenon of decoherence, in which quantum states are disrupted by interactions with the surrounding environment, posed a major obstacle. Scientists needed to develop methods to preserve entanglement and accurately transfer quantum information over increasingly large scales. The turning point came with the development of quantum repeaters and advances in quantum communication technologies. Quantum repeaters are devices that extend the range of quantum communication by creating and storing entangled particles at intermediate points along a transmission path. These devices effectively act as relays, ensuring that the entanglement remains intact over long distances. In recent years, researchers have achieved remarkable milestones in quantum teleportation. In 2015, a team of Chinese scientists successfully teleported quantum information over a distance of 100 kilometers using optical fibers. 2 years later, in 2017, another Chinese team took this achievement to unprecedented heights by teleporting quantum states between ground stations and a satellite orbiting Earth, covering a distance of over 1,200 kilometers. This breakthrough demonstrated the feasibility of space-based quantum communication and opened the door to a new era of secure and instantaneous information transfer. Fast forward to today, and the field of quantum teleportation has reached an incredible new milestone. In 2023, an international collaboration of scientists successfully achieved quantum teleportation over intercontinental distances, marking a watershed moment in the history of physics. This achievement was made possible through the use of advanced quantum networks, cutting-edge entanglement distribution systems, and revolutionary techniques for error correction. So, how does quantum teleportation actually work? The process involves three key components: entangled particles, a quantum state to be teleported, and classical communication. First, two particles are entangled, creating a shared quantum state. One of these particles is sent to the destination while the other remains at the sender's location. Next, the quantum state of a third particle, the one to be teleported, is combined with the particle at the sender's location. This combination is achieved through a process called a Bell state measurement, which effectively destroys the original quantum state and encodes its information onto the entangled pair. Finally, the results of the Bell state measurement are sent to the destination via classical communication, such as radio waves or optical signals. Upon receiving this information, the particle at the destination can be manipulated to replicate the original quantum state. Importantly, the original quantum state is not copied. It is effectively recreated at the destination while the original information is destroyed in the process. The implications of this achievement are profound and far-reaching. Quantum teleportation has the potential to revolutionize communication by enabling ultra-secure quantum networks. Unlike classical communication systems, which are vulnerable to eavesdropping, quantum networks rely on the principles of quantum mechanics to ensure the integrity of transmitted information. Any attempt to intercept or tamper with a quantum signal would immediately disrupt the entanglement, alerting the parties involved. This level of security has significant applications in fields such as banking, government communications, and defense. Imagine a world where encrypted messages are not only unbreakable but also immune to future advances in computing power, including the emergence of quantum computers. Quantum teleportation could make this vision a reality, safeguarding sensitive information in an increasingly interconnected world. Beyond secure communication, quantum teleportation holds enormous promise for the development of quantum computers. These powerful machines, which leverage the principles of quantum mechanics, have the potential to solve problems that are currently intractable for classical computers. However, building large-scale quantum computers requires the ability to connect and synchronize multiple quantum processors. Quantum teleportation provides a means of achieving this, enabling the creation of distributed quantum computing networks that can tackle complex tasks with unprecedented speed and efficiency. Furthermore, quantum teleportation could pave the way for new technologies that are currently beyond our imagination. From quantum-enhanced sensing and imaging to breakthroughs in materials science and medicine, the possibilities are virtually limitless. The ability to transfer quantum information instantaneously could also have profound implications for our understanding of the universe, allowing scientists to probe the fundamental nature of reality and explore questions that have long eluded answers. Despite these remarkable achievements, it is important to note that quantum teleportation is still in its early stages. Many technical challenges remain, including the need to improve the efficiency and reliability of quantum networks, reduce the impact of noise and decoherence, and develop scalable systems for entanglement distribution. Nevertheless, the progress made over the past 27 years is a testament to the power of human ingenuity and perseverance. From the initial theoretical proposal to the successful demonstration of quantum teleportation over intercontinental distances, scientists have pushed the boundaries of what is possible, unlocking new frontiers of knowledge and discovery. As we look to the future, it is clear that quantum teleportation will play a central role in shaping the technologies and systems of tomorrow. It represents a paradigm shift in our understanding of information, communication, and the fabric of reality itself. The journey to achieving quantum teleportation has been a long and challenging one, filled with moments of doubt, setbacks, and breakthroughs. But it is precisely this journey that makes the achievement so extraordinary. It reminds us of the boundless potential of human curiosity and the transformative power of science to change the world. In the coming years, we can expect to see even more groundbreaking advancements in the field of quantum teleportation. As researchers continue to refine their techniques and explore new applications, the dream of a fully functional quantum internet, distributed quantum computing, and even quantum-enhanced space exploration may become a reality. For now, we stand at the threshold of a new era, one in which the boundaries between science fiction and science fact are becoming increasingly blurred. Quantum teleportation is no longer just a theoretical concept. It is a tangible achievement that holds the promise of revolutionizing our world and unlocking the mysteries of the universe. Let this achievement serve as a reminder that the impossible is often just a matter of perspective, and that with dedication, collaboration, and an unwavering commitment to discovery, humanity can achieve feats that were once thought to be beyond reach. The era of quantum teleportation has begun, and the future is brighter and stranger than we could have ever imagined. The foundations of quantum entanglement, a deeper dive. Quantum teleportation fundamentally relies on quantum entanglement, one of the most baffling phenomena in physics. To truly understand its significance, we need to examine the underlying principles in greater depth. Entanglement isn't just a quirky feature of the quantum world, it's a cornerstone of how particles interact at the most fundamental level. When two particles become entangled, their properties become inseparably linked. Imagine a pair of dice that always roll the same number, regardless of how far apart they are or how many times you throw them. This analogy, while oversimplified, illustrates the spooky coordination that entangled particles exhibit. Measure one particle, and the outcome of its partner becomes instantly determined, even if they are light years apart. What makes entanglement so extraordinary is that it seems to violate our classical understanding of causality and locality. In the macroscopic world, information cannot travel faster than the speed of light. Yet, in entangled systems, information about the state of one particle appears to be shared with its partner instantaneously. This phenomenon doesn't involve any faster-than-light communication, as no usable information can be transmitted directly. Instead, entanglement reveals how fundamentally interconnected the quantum universe is. Over the years, experiments like the groundbreaking Bell test experiments have confirmed that entanglement is real, robust, and incompatible with classical explanations. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their pioneering work in experimentally verifying quantum entanglement. Their contributions laid the groundwork for technologies like quantum teleportation, which rely on harnessing and manipulating entangled systems. How quantum teleportation can revolutionize communication. Quantum teleportation isn't just an abstract phenomenon confined to laboratories. Its practical applications could completely transform how we communicate and exchange information. One of the most exciting possibilities is the development of a quantum internet, a network that uses quantum states to transmit information securely and efficiently. Unlike classical networks, where data travels through physical cables or radio waves, quantum networks leverage the properties of entanglement to enable instantaneous and unhackable communication. At the heart of a quantum internet lies the concept of quantum key distribution, QKD. QKD allows two parties to generate a shared encryption key using entangled particles. Because any attempt to intercept or measure the entangled particles would disturb their quantum states, eavesdropping becomes detectable. This makes QKD an ideal solution for transmitting sensitive information such as financial transactions, government communications, or medical data. But quantum teleportation takes this concept even further by enabling the transfer of quantum states directly. Teleportation could eliminate the need for physical transmission of data altogether. This would result in unprecedented levels of security and efficiency, particularly for applications that require instantaneous decision-making or coordination, such as autonomous systems or global financial markets. For example, imagine a future where international banking systems rely on quantum teleportation to execute transactions in real time, with zero latency and absolute protection against cyber attacks. Or consider the implications for global communication, where language translation, video conferencing, and data sharing happen seamlessly, without delays or vulnerabilities. The role of quantum teleportation in computing. Another area where quantum teleportation is poised to make a significant impact is quantum computing. Quantum computers differ fundamentally from classical computers in that they use qubits, quantum bits that can exist in multiple states simultaneously. This property, known as superposition, allows quantum computers to perform calculations that would be impossible for classical machines. However, building large-scale quantum computers comes with challenges, particularly when it comes to connecting and synchronizing qubits across vast distances. This is where quantum teleportation becomes invaluable. By enabling the transfer of quantum states between distant qubits, teleportation can serve as the backbone of distributed quantum computing networks. Such networks would allow quantum processors to work together on complex problems, effectively creating a global quantum supercomputer. These systems could tackle challenges ranging from drug discovery and climate modeling to cryptography and artificial intelligence. For instance, quantum simulations could revolutionize materials science by accurately predicting the properties of new compounds, paving the way for breakthroughs in energy storage, nanotechnology, and medicine. In addition, quantum teleportation could solve a critical bottleneck in quantum error correction. Error correction is essential for maintaining the stability of quantum systems, which are notoriously prone to decoherence. By teleporting quantum states to error-free qubits, researchers could preserve information and extend the operational lifespan of quantum processors, bringing us closer to realizing practical, fault-tolerant quantum computing. Breaking the barriers, challenges in quantum teleportation. While the achievements in quantum teleportation are undeniably impressive, the road to widespread implementation is far from straightforward. Several technical, logistical, and theoretical challenges must be addressed before we can fully harness this technology's potential. One major hurdle is scalability. Current experiments in quantum teleportation typically involve a small number of particles and require highly controlled laboratory conditions. Scaling up these experiments to create functional quantum networks will require advances in hardware, such as high-efficiency photon detectors, stable sources of entangled particles, and error-resistant quantum repeaters. Another challenge is the fragility of quantum systems. Entanglement is highly susceptible to interference from the environment, a phenomenon known as decoherence. Even the slightest interaction with stray particles or electromagnetic fields can disrupt the quantum state, rendering the system unusable. Developing robust techniques to mitigate decoherence is essential for enabling reliable quantum teleportation over long distances. Additionally, there are limits to how far quantum entanglement can be distributed using current technologies. Optical fibers, for example, suffer from signal loss over large distances, making it difficult to maintain entanglement across continents or between Earth and space. Researchers are exploring alternative methods, such as using satellites or free space optical links, to overcome these limitations and extend the range of quantum communication. Finally, the theoretical implications of quantum teleportation continue to spark debate among physicists and philosophers. Questions about the nature of information, the role of consciousness, and the boundaries of quantum mechanics remain unresolved, challenging our understanding of reality itself. A philosophical perspective. What does teleportation mean for reality? Quantum teleportation isn't just a scientific breakthrough. It's a profound reminder of the strange and interconnected nature of the universe. By allowing information to be transferred instantaneously, it challenges our classical notions of causality, locality, and the flow of time. One of the most intriguing philosophical questions raised by quantum teleportation is, what does it mean for information to exist independently of physical matter? In classical systems, information is always tied to a physical medium, such as ink on paper or electrical signals in a computer. But in the quantum realm, information can exist in a purely abstract form, encoded in the correlations between entangled particles. This raises profound questions about the nature of consciousness and identity. If quantum information can be transferred from one location to another without physically moving the particles, could the same principles apply to the human mind? Could teleportation one day enable the transfer of thoughts, memories, or even entire consciousnesses? And if so, would the teleported consciousness still be you, or would it be a perfect copy with no connection to the original?